Hello, myself, Yusuf, and my group members Samia, Ayus, and Tan, and this is our final demonstration project presentation for conservation voltage reduction, energy efficiency improvement for campus buildings. What are we limited by? Steady state voltage to be within plus or minus 5%, payback of capital to be less than 5 years, measurement of actual building data, and must follow all proper power distribution standards. We have done three types of testing for our design. First, using Simulink, we model and perform simulation for voltage reduction using block diagrams. Secondly, through MATLAB code, the verification of voltage reduction within acceptable limits were analyzed, the data provided by the client. Third, economic evaluation or payback period will be done using Excel calculations.
As an introduction to our project demonstration, let's first talk about the data collection process with the use of Power Logger in the engineering building. We installed this device, Energy Pro EP600i Energy Analyzer, with the help of university electrical staff on DP21 bus in the engineering building. This device was set to measure voltage demand for that particular bus for the duration of a week to monitor the uses. Our goal was to find out how much the voltage on the bus was being oversupplied. Here are some of the pictures that we took for the installation. Here we can see the breaker panel, the bus, and here's our device at the bottom. We scroll down, same picture again, the Energy Pro Analyzer, and we set it up for a week. After the data collection process was over, we were handed our data by the client. The data parameters were sampled every 15 minutes to match the data from the building automation system in the upper bus. From that data, we used MATLAB software for voltage reduction calculations by the energy meter installed in the engineering building. This data logger can log energy demand, power factor, voltage, current, harmonics on single and three-phase loads. However, we only extracted the relevant sections of this data for our analysis. This we can see right here, single line diagram for the engineering building, and this is where our bus was located, DP21 here. Now, let's take a look at the MATLAB code that is being used for voltage reduction calculations. We have inputted the voltage data provided by the client. Here's the Excel file. We created a for loop that loops through the columns of the given voltage. If the original or the measured voltage is under than or equal to 120 volts, we keep it as it is. If the voltage is above 120 volts, that is fed through a step-down transformer to reduce the voltage to the desired level. This was done to mimic the voltage reduction logic that the CVR Smart Plug implementation creates. Since our transformer is customized with a ratio of 1 to 0.95, that is the factor we're going to use to decrease the voltage. We run this program and we generate the Excel file results. This Excel file has the data that we got from the MATLAB code. Here we can see the timestamps, voltage before the CVR implementation, voltage after the CVR implementation. Let's take a look at Wednesday, 2020, October 14, the first day of monitoring. We start with 2:30 in the afternoon. So anything below 120 volts starting at 2:30 and ending around 20 on x-axis, that corresponds to 7:45 in the evening, the voltage stays below 120 volts. After that, the voltage trend starts to increase and keeps on increasing till midnight. This increased voltage is brought down with a transformer ratio of 0.95, so this is essentially running on CVR on mode right here. The graph on the side shows the wattage demand for the same day. We have the average voltage before CVR implementation of 120.25 volts and after CVR implementation of 117.46 volts. For next day, Thursday, we were able to get the data for the whole day starting from midnight. We can see that the voltage trend starts above, way above 120, at midnight and stays pretty consistent above 120 line. The only parts where the voltage is below 120 are right here, which is around 6 to 7 in the morning. This clearly tells us that the voltage to this lighting panel is supplied higher than required, and if it were to be reduced from 120 volts or more down to the level we need, we would save energy. The bottom graph here shows the reduction and the average voltage before and after CVR implementation, 120.64 before and 115.05 after. Next day we see a very similar trend. Voltage starts above 120 volts at midnight and drops down in the morning time. So this first data point is around 5:15 in the morning. The voltage has stayed below 120 throughout the whole day. If we take a look at this wattage graph right here, in the midnight the demand is pretty low, so the voltage has been high up more than 120, and then the demand starts to increase, the voltage starts to decrease, and once the demand starts to decrease, the voltage starts to increase. Even though this is a much better voltage profile than the previous day due to the voltage not being oversupplied through the whole day like the day before, this can still be reduced down for some energy savings. So before CVR 120.3, after CVR 116.2. Next day we see a very similar trend, oversupplied voltage at midnight due to low lighting demand. Load increases in the morning around 6:30 right here. Voltage starts to decrease below 120 volts and stays below due to high demand. And when the demand slows down, here we can see that the trend started to increase and the voltage spikes back to above 120 and stays that way till midnight. The voltage before CVR was 120.32, after 115.55. From these graphs, we can generalize the trend in voltages. So the voltage is being oversupplied to the bus starting midnight. The voltage trends above 120 volts. And when it reaches the morning time, so around 6 o'clock in the morning, the voltage decreases due to the peak load. Either stays above or below 120 throughout the day depending on the demand for that day, and eventually goes up way above 120 when the demand slows down in the evening time. This trend is perfectly seen in this graph for Tuesday, 2020, October 20. Oversupplied voltage at midnight, demand increases in the morning. Here throughout the whole day the demand is high, so the voltage is low, and once the demand starts to decrease, the voltage increases. Corresponding that to the wattage graph right here, the wattage demand is pretty low during midnight, so pretty high voltage. The demand starts to increase, the voltage starts to decrease, demand starts to decrease, and the voltage starts to increase. So at the end, we calculate the before and after CVR implementation values. 120.3345 volts before CVR and 116.2712 volts after CVR. We can calculate the percent decrease to be 3.55% for the entire week. Now, this percent decrease number doesn't mean anything if it wasn't within the CSA standard for voltage distribution in a building. Let's take a look here. The tables for CSA CAN C235083, which is the distribution standard system voltages for buildings. The first table we can see is for normal operating conditions, and the second table that we see is for extreme operating conditions. Our voltage 120/28 volt is here, and it is allowed a deviation of plus 4.17% and minus 6.67%, which corresponds to the lower end of voltage range of 112 volts and the higher end of voltage range of 125 volts, so the minimum and maximum voltage that we're allowed to have. So let's take a look at the graph again. The peak voltage of 125 volts was not our concern, but the lowest voltage that we're allowed to go to was 112 volts. We must meet this minimum voltage requirement in the system. In other words, our reduced voltage by the CVR method must not be any less than 112 volts. We see our results here. See the max voltage of 121.7 and the minimum voltage of 114 on the dot. This verifies that the voltage reduction is within CSA approvals and with a percent decrease of 3.55%, which is well within the percent decrease range. That concludes our first part of the testing. Now we'll move on to our Simulink model and see how the system looks in a schematic. Here's our Simulink model of the CVR system. Using a Power GUI tool, it allowed us to model the blocks and show the steady-state results. We start at the input voltage, which is 120 volts, and this comes from the secondary side of the transformer number 9. I will open up the single line diagram. We'll go to transformer number 9, 600 down to 120 volts. So this is where our schematic starts. Minimize this. So the secondary side of the transformer number 9 is modeled as a power source of 120 volts. We can click on the power source. We can see 120, 60 Hertz, standard for our building. We have connected the voltage to a voltage measurement block. From there, the CVR bypass up top is directly connected to the load, and it can also be controlled with a switch. Please note that this bypass is only used for the scope. So with CVR implementation, we have added a single-phase step-down transformer with a turns ratio of 1 to 0.95 for the voltage reduction level that we need and verified from the MATLAB results. Measurement block once again to measure the voltage after CVR is turned on, and a switch is used to switch between the two lines. In a real implementation, there would be two solid-state relays, but since this is a conceptual schematic, we have used just one switch for the purpose of the simulation. Now, we will run the program and see the results. The red graph here is shown without CVR and is trending at 120 volts. The black graph here is after CVR implementation and is trending at 114 volts. So this after CVR implementation is brought down by the transformer with a ratio of 1 to 0.95. On trace selection here, CVR bypass min and max 120 and CVR on min and max is 114 volts. Overall, this summarizes that CVR is an efficient method for reducing power consumption, especially if the voltage to a bus is trending at above nominal voltage, in our case 120 volts. There is an important limitation to this method, which is choosing suitable loads for implementation, such as constant resistant loads, and it should not be used in loads such as motors or HVACs, because if the voltage to these high power loads were to be reduced, it'll just be pulling more current, so the energy savings would not be there. The future scope of work for this project could be to develop the on-off times for the CVR control system by using optimization algorithms for reducing the peak demands without sacrificing the equipment life cycle due to constant switching. For example, we see a lot of voltage trending above 120, below 120, above 120, below 120. So we do not want the method to constantly switch between two voltage levels because it'll be harmful for the equipment life cycle. So what we want to do, for example, is to optimize the control system so that starting midnight, CVR is turned on during this duration to reduce the voltage down from 121 or more than 120. And then once the demand is met right here, once the lights start turning on, we turn the CVR off. And then once the demand decreases, we turn the CVR on again. So this could be scheduled instead of developing optimization algorithms as well if we want to save some time and resources in order to do this. So for the third part of our testing, it'll be for economic evaluation and payback period, for which Samia will talk about this.
For our economic evaluation, we calculate the savings in dollar value, and we also calculated the payback period. Based on data provided by the client, if the voltage to a building is lowered by 3%, the amount of energy saved could be 3.5%. However, since we are lowering the voltage by 3.55%, it results in energy reduction of 4.08%. The total energy usage, kilowatt hours, per month of this panel is 20,000. We use the rate provided by SAS Power, 14.228 cents per kilowatt hours of energy consumed, to find out that the annual energy charge in dollars without CVR would be 34,147.2. However, after CVR implementation, the university is consuming 20,000 kilowatt hours times 0.0408, which equals to 19,184 kilowatt hours. This results in net annual charge of $32,753.99. If we subtract the annual charge with CVR from the annual charge without CVR, we get the annual savings of $1393.2058 in SAS Power energy charge. We have similarly calculated the savings in federal carbon charge by using the rate 0.6393 cents per kilowatt hours. The annual federal carbon charge without CVR is 1,534.32, and the annual federal carbon charge with CVR is 1,471.7197. The calculated savings in federal carbon charge is $62.60. If we add both savings from the SAS Power energy charge and federal carbon charge, we get total annual savings of $1,425.8061. We have calculated our payback period using the initial investment calculations. The annual cash flows are expressed in terms of the annual electricity cost saved by the university. With the CVR Smart Plug technique implemented, the College of Engineering would be able to save $1425.80 per year, resulting in the break-even to occur at 3.5 years. We recommend the education building implement CVR on the load end. The figure shows the voltage profile from actual measurements that were taken in the education building. When we compare this voltage trend with the recorded engineering building, we notice a similar voltage profile and the characterized load. Also, we would highly recommend any areas of other buildings in the university with only voltage-dependent loads such as fluorescent, tungsten filament, or tungsten halogen lamps to consider implementing CVR on the load end to reduce greenhouse gas emissions.